Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at Taylor series and polynomials. So we're going to start by looking at linearization. Lx here is a linear approximation to some function fx. So what's happening here? We will have some function here, might look like this, and we have some point A, and we're approximating the curve with a linear function at that point. And hopefully you see this formula looks a whole lot like the equation of a tangent formula. So the idea is that this curve and the blue line will be similar in that they have the same value at this point, same value of the function, but also the same first derivative. So this line is basically as good as we're going to get at approximating the curve. And the reason we might want to do this is linear functions are a lot easier to work with than many other functions. So let's look at an example where we use linearization to estimate the square root of 32. So we're square rooting here. So the function in which I'm interested is square root of x. So what we're going to do is we're going to estimate root 32 around x equals 25. Why are we choosing 25 of all possible values? Because square root of 25 is a whole number. We don't need to estimate it. We'd hate to have to estimate all these in order to come up with another estimation. So let's first come up with this approximation linear polynomial. So at x equals 25, we have f of 25 equals 5. Now, the derivative of the square root of x is 1 over 2 root x. So we have that the derivative at 25 is 1 over 2 times 5, which is 1 over 10 or 0.1. So the linear polynomial we're going to use for this one to approximate root x is going to be L, we usually call it L of x equals f of a, which was 5, plus f dash of a, which was 0.1, and then we have x minus 25. So how does that help us estimate root 32? Well, what we're going to do is now just simply substitute in 32. So the estimation we get is 5 plus 0.1 times 32 minus 25, which is 7. So the approximation we get is about 5.7. That's actually not bad. Root 32 is about 5.66. Obviously, the further away this value was from this value, the worse the approximation's going to get. But here, we approximated root x with a linear function. So let's look at some higher order Taylor series. So the idea behind Taylor series is we want to approximate a function with a polynomial because polynomials have nice properties. They basically use the 4 operations plus exponentiation, they're continuous, their graphs are smooth, etc. and so on. So it would be great if we could just stick to lines, if we could take any function and accurately estimate it with a line. But lines don't do a very good job of estimating functions. So we find a polynomial. So the polynomial can have n terms. It can have as many terms as you want. And the more terms it has, the more accurate a representation it is. So the Taylor series polynomial follows this form here. And the idea is if we follow this form here rather than just getting some random polynomial, if you use n terms, the polynomial at the point x equals a will have the same value as the function, but it will also have the same first n derivatives. So if your polynomial is of degree 4, it will have the same first, second, third, and fourth derivatives as the function. So these polynomials, they basically do a decent job or sometimes a really good job of estimating the curve around a point where x equals a. So they might not be a good representation of the curve throughout the whole real line, but they'll be good in the neighborhood of a. Now, if a equals 0, so if we find an estimation of a function close to 0, we call this a Maclaurin series. Maclaurin series are way easier to work with. I mean, you can probably see that because of all these a terms, if a is not 0, this polynomial gets complicated very quickly. So we're going to look at an example where we find the Maclaurin series for e to the power of x. So Maclaurin series means we're going to do it around a equals 0. So what would be our polynomial? So Pn of x, it will be f of a, so a was 0. Now f of 0, e to the power of 0 is 1. Now f dash of a, remember the derivative, in fact all derivatives of ex is just ex. So the derivative evaluated at 0 is e to the power of 0, which is also 1. And then again, a was 0, so this will be x minus 0. The next term will be the second derivative of e to the x evaluated at 0. That is, again, e to the power of 0, which is 1. So it will be 1 over 2 factorial x minus 0 squared. The next term. So the third derivative of e to the x evaluated at 0 is e to the power of 0. All of these derivatives evaluated at e to the power of 0 are going to be 1. So the next one is 1 over 3 factorial x minus 0 cubed. And as you can probably guess, the next term is going to be 1 over 4 factorial times x minus 0 to the power of 4. And this can go on forever and ever if you want. So just making this a bit easier to read, it'll be 1 plus x. The next term is x squared on 2 factorial. The next term is x cubed on 3 factorial. So this polynomial can go forever. You might see it written in sigma notation. So this just means you start at k equals 0. So first up we have x to the power of 0 over 0 factorial. Note 0 factorial is 1, that's how you got the 1. The next term would be if k equals 1, so it would be x to the power of 1 on 1 factorial, which gives us that. Then if k equals 2, x to the power of 2 on 2 factorial, and so on. This means you sum them all up, and you can go forever and ever. So this is the Taylor series of e to the x around 0, and we usually call them Maclaurin series. So this is the Maclaurin series of e to the x, and it's really helpful. This can help your calculator, for example, calculate values of e to the power of x. If you want to know e to the power of 2, for example, you can just substitute into here. Of course, your calculator would only use a certain number of terms, can't go on forever, but it just makes the calculation easier. But of course, because we did this around a equals 0, this polynomial is much, much better at approximating e to the x close to 0. Not really that good if the value that you're substituting for x is far away from 0. All right, let's look at one more example where we develop a Maclaurin series. So let's find the Maclaurin series for cos of x. So it's always going to be around 0 for a Maclaurin series, so we start off with cos of 0. Then the next term is going to be the derivative of cos, which is minus sign, evaluated at 0 over 1 factorial. It'll be times by x minus 0, so just x. The next one will be the second derivative of cos evaluated at 0. So the derivative of minus sign is negative cos. So it'll be negative cos of 0, all divided by 2 factorial times x squared. All right, what's the derivative of negative cos x? Well, it's back to sine. So the next term will be sine of 0 over 3 factorial times x cubed. And it sort of goes on in this cycle. The next one, it will be cos of 0 divided by 4 factorial times x to the power of 4. So we're going to keep going cos 0, negative sine 0, negative cos 0, sine 0. And then we get back to the start, repeat this cycle again. So it's going to go on forever and ever like that. Now notice that cos 0 equals 1. So first term is 1. All of these sine zeros equal 0. So anything with an odd pair of x is actually going to cancel out. But this one here is going to be negative 1. So that'll be negative 1 on 2 factorial x squared. We'll just write negative x squared on 2 factorial. And then the next even power, cos 0 is 1, so that'll be positive 1 times x to the power of 4 over 4 factorial. It's going to go on like this. So you can probably see the pattern. Only even powers of x on top, and whatever the power is, that factorial goes on the bottom, and every second term is positive and every other term is negative. So that is the Maclaurin series for cos x. And this is how your calculator actually calculates values for cos where x is close to 0. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.